Hello, everybody. Welcome to week 6. So our content for week 6 basically consists of another concept relating to commuting elements and elements that don't commute with each other. Last week we talked about centralizer of an element. And this week we're going to talk about a very closely related concept, and that's the concept of conjugacy in groups. So our two short lectures this week basically will have the same theme, which is conjugacy. And this first one, I'll try to explain what it means for two elements in a group to be related to each other by this relationship of conjugacy. And then in the second one, we'll sort of prove our main theorem, which connects the conjugates of an element to the centralizer of that element, and which applies, again, our friend Lagrange's theorem. Okay, so the context is sort of a bit abstract here. We're in an abstract group. We look at a few examples as well to try to bring this concept down to earth a little bit. But I guess our reasoning is mainly in the abstract context. So we're in a group. We've got a group G. We've got an element X that we regard as being fixed. So imagine that you've got some group G. You're picking an element X of G and you're sort of concentrating on that element. And then G is just any other element of G. Okay, so X is sort of fixed, but G is sort of arbitrary. Okay, so we know what we mean by saying that G commutes with X. It means that when we compose X with G or G with X, that those two elements are the same. Okay, and we know typically the situation would be that our chosen element X will commute with some G's and not with other G's if we're in a non-abelian group and if X is not in the center. Okay, the same language or same other ways of saying the same thing. G commutes with X, or G centralizes X, or G belongs to the centralizer of X, all mean that Gx is equal to Xg in the group G. Okay, fine, that's nothing new there. That's just recalling some language. Observation is that if we have the situation where X and G commute with each other, so that this equation, xg equals gx, is satisfied, then we're in a group. So we can rearrange that equation by composing both sides of it on the right with the inverse of g. Okay. If we do that, then on the left-hand side, the g inverse and the g cancel each other and we just get x. But on the right-hand side, we've got gx, g inverse. Okay. So the statement xg equals gx is equivalent in the group to the statement that x equals gx, g inverse. Okay, and of course you can get from this one back to that one by just composing both sides of this version on the right with the element g itself. Then you'll have xg equals gx. Okay, so fine. What are we saying? We're saying that, well, yet another way of saying that x commutes with g is to say that x is equal to the element g composed with x composed with g inverse. Okay, and I guess, okay, this is sort of not so surprising because if we look at the form of this element, gx, g inverse, if g and x commute with each other, then we can just move the g here into the center of this product of three things and it'll cancel the g inverse and we'll just be saying x equals x. If g and x don't commute with each other, then we can't do that. And in that case, gx, g inverse is not the same element as x. Okay, it's something else. And, it's something else in the group. We can't say a whole lot more because we don't know what our group is. But the element gx, g inverse, I guess it's related to x by the act of composing x on the left with some element and on the right with the inverse of that element. Okay, so if we were in a commutative setup, the g and the g inverse here would cancel each other and this would just be x. If we're in a non-commutative setup, this may be different from x. That's the kind of concept that conjugacy is about. Okay, so as g moves through the elements of the group G, this thing, gx, g inverse, sometimes it's equal to x if g commutes with x. Generally, it's not. And as we let g sort of move through all the elements of the group G, this expression gx, g inverse will run through some of the elements of the group. And the elements that arise as gx, g inverse for different choices of the element little g are referred to as the conjugates of the element x in G. Okay, so bear in mind here, x is considered to be fixed. G is considered to be sort of varying through the elements of the group. As G varies through the elements of the group, this conjugate, gx, g inverse, sometimes it's equal to x if g commutes with x, other times it's not. It'll take, it'll represent different elements as G varies, and the elements that occur that way are called the conjugates of x in G. So a conjugate of x in G is any element of the form gx, g inverse, where G is some element of the group. Okay. That's what conjugates are. Why we care about them maybe is not yet so clear, but we will hopefully come to some good reasons to care about them. For the moment, I guess what you should take from this particular slide is just the definition of what it means to be a conjugate of an element X in a group. Okay, this is a not obviously interesting concept. So by way of trying to sell it as something that might be interesting, let me recall that it's actually probably not entirely new to us. There are contexts in which we've seen this before. So here is some context and some examples. So really the first item here is intended to be the context, and the second item is an example more closely related to examples of groups that we've been studying lately. So supposing that we're in the group GL3R, invertible 3x3 matrices with real entries. Okay, so as you know, these things represent invertible linear transformations of three-dimensional space. And when you're studying linear algebra, that's kind of what you care about in terms of matrices. Here we care about the fact that they form groups under the algebraic operation of matrix multiplication. But we know from the definition we've just seen in the previous slide that if A is some fixed matrix that we choose in here, so it's some invertible 3x3 matrix, then the conjugates of A in GL3R, if we believe the definitions in the last slide, are all matrices that we can get by taking A, multiplying it in front using matrix multiplication by some invertible matrix P, and behind by the inverse of P. So anything of the form PAP inverse, where P is any invertible matrix, any element of our group. And we've seen that before in linear algebra. Okay, or if it looks vaguely familiar to you and you want to remind yourself, just go back and have a look at some notes from linear algebra courses. We know that the matrices of the form PAP inverse are exactly those matrices that represent the same linear transformation that A does with respect to different choices of basis, okay, where P represents some sort of change of basis matrix from one basis to another. So what we're saying here is that in the context of the definition of conjugacy that we've just seen, two matrices in GL3R are conjugate to each other in that group, exactly if they represent the same linear transformation and differ from each other only by a choice of basis. So in the case of GL3R, there's sort of like a geometric interpretation of this concept of conjugacy. Two matrices are conjugate to each other if they represent the same linear transformation with respect to different choices of basis. So somehow what they do geometrically to R3 as linear transformations is the same thing, just with respect to different choices of basis. Okay, so that's a kind of a, I don't know, more geometric definition, at least, if not more concrete definition of the notion of conjugacy for 3x3 matrices and for square matrices generally. Unfortunately, it's just not true that in every group we can attach some sort of meaning to the notion of conjugacy that resembles that we can relate it to something else, like the geometry of some situation. Sometimes we can, sometimes we can't. Another example of a situation where we can is the symmetric groups, the groups of permutations, and we will look at that next week. But here, at least in the case of sort of this connection to linear algebra, we can give a meaning to conjugacy apart from just purely at the group theory level. We can say that it means something geometrically as well. Okay. Here's another example, and again, it's a group that has a geometric meaning. If G is our friend G6, which has appeared in a lot of these lectures recently, the group of symmetries of the equilateral triangle. So here's our equilateral triangle with the axes of reflection labeled and the three vertices labeled. And we know that we have 6 elements here. We have the 3 rotations, the identity rotations through 120 and 240 degrees, and we have the 3 reflections and the 3 axes that are indicated there. Okay, so here, using the definition from the previous slide and using the group table, if you don't have it handy, it's listed in some of the notes from recent lectures, we can actually just sort of figure out what are the conjugates of each element. Okay, so if you start with the identity element and ask ourselves what are the elements that we can get by taking some element X and looking at, or some element G, let's say, and looking at G composed with identity, composed with the inverse of G. Well, everything commutes with the identity. So in all such cases, the G and the G inverse are going to cancel each other, and we're just going to be left with the identity element itself. So the conjugates of the identity element, there's only one, just the identity element itself, and that is true for the identity element in every group. It commutes with everything else, so its only conjugate is itself. There's no G that doesn't commute with it that could give G identity, G inverse, to be something other than the identity. Okay, so that's fine. That's the conjugate of the identity. If you take the rotation through 120 degrees, I assert or claim that the only conjugates of that element are itself and the other rotation, the other non-identity rotation, which is through 240 degrees. And okay, to see that, if we conjugate the rotation through 120 with another rotation, we're going to get a composition of rotations, so we're going to get a rotation. Also, we know that the rotation through 120 degrees commutes with the other rotations. So by conjugating rotation through 120 with any of the 3 rotations, we're just going to get that element itself back. The rotation through 120 does not commute with the reflections. So if we take T composed with rotations through 120, composed with the inverse of T, which is T itself, for any one of the three reflections, we'll find that in fact what we get is the other rotation, the rotation through 240. Okay? So I'm not claiming that this is completely obvious. I'm claiming that it should be checkable by looking at the group table for D6 and just sort of confirming it by just calculating the products there and confirming what you get. Okay, so the only conjugates of the rotation through 120 are itself and its partner, the other non-identity rotation. If we take one of the reflections, and for example, if we take TL, the reflection in the vertical axis here that passes through the vertex A, TL commutes with itself and with the identity, but not with anything else. So if you conjugate TL by the rotation through 120, for example, take rotation through 120, compose with TL, compose with the inverse of rotation through 120, which is rotation through 240. Again, you can just check the products and confirm that that element is Tn. If you take the rotation through 240, compose with TL, compose with the inverse of the rotation through 240, you will find that you get the reflection in the line N. And again, I'm not claiming that we should be able to sort of see this instantly by glancing at the diagram here. I'm claiming that it can be verified with a short calculation. But what we find is that the conjugates of the reflection TL are exactly all three reflections. If you conjugate TL with itself or with the identity element, you get TL. If you do it with the rotations through 120 and 240 respectively, for example, you get TM and TN. You can also get those by conjugating TL with different reflections. So this example it's just really an example to kind of keep track of everything that we've done on the last slide and use the definition to calculate the conjugates of various elements. What we notice after we've done this, and again, I'm not claiming that this is supposed to be something that's obvious or that we're supposed to immediately see that it's something that holds in more generality, but we can observe the conjugate of the identity element is just the identity element itself. The rotation through 120 and rotation through 240 both occur as conjugates of rotation through 120. And the remaining three elements, the three reflections, all occur as conjugates of TL. Okay? So we can notice that every element of the group, every element of D6 belongs to exactly one of these three categories. Either it's conjugate to the identity, that happens only if it is the identity already itself, or it's conjugate to the rotation through 120, that happens if it's a rotation but not the identity, or it's conjugate to TL, and that happens if it's any one of the three reflections. So for every one of the elements of D6, it's a conjugate of exactly one of the identity, the rotation through 120, and the reflection TL. Okay, so we have a sort of partition of the full set of 6 elements into 3 parts, with one part consisting only of the identity, another consisting of the 2 non-identity rotations, and another one consisting of the 3 reflections. These 3 sets are called the conjugacy classes in D6. And what we're seeing here in this example is indeed an example of a sort of general phenomenon that the group falls into various pieces according to which elements are conjugates of each other. So we're going to develop that idea a bit more now and a bit more in the second lecture for this week. But first, I'll just mention something that isn't really completely documented in the lecture notes, at least not quite in this way, which is that the relationship of conjugacy is an equivalence relation on any group. So if you haven't been thinking about equivalence relations recently, it might be a good time to remind yourself of what they are, but we'll recall it anyway, when we show that conjugacy on a group is an equivalence relation. Okay, what do we mean by that? Well, a relation, first of all, on some set, for example, a group is a statement that one element can be related to another, or that certain elements can be related to certain others. So we're going to use the symbol, this twiddle symbol, this tilde, to write that one element is conjugate to another. So we'd write x twiddle y like this, x related to y, to mean that y is a conjugate of x. Okay, and according to our definitions so far, what it means to say that y is a conjugate of x in a group G is that the element y is equal to gx, g inverse, for some element g of G. Okay, that's what x related to y means. That there's some g in G for which y is equal to gx, g inverse. Okay, so if we claim that this relation is an equivalence relation, to confirm that statement, we have to show 3 things. We have to show that it is reflexive, which means that every element is related to itself. It's symmetric, which means that if y is a conjugate of x, then x is also a conjugate of y. And we have to show that it's transitive, which means that if x is related to y and y is related to z, then x is related to z. Okay, so let's take these 3 things one by one, as we generally do for equivalence relations. So to show that this relation is reflexive, we need to show that x is conjugate to itself for every element x of G. To show that x is conjugate to itself, you need to show that there's some element G in the group with the property that x is equal to gx g inverse. Any element g that commutes with x will do that trick. So in particular, taking x itself will do it, or taking the identity element will do it. But certainly we can observe that x is equal to x inverse, because the x and the x inverse cancel each other here. And this right-hand side of this statement is just equal to x. So x can be represented as a conjugate of itself by just writing x inverse. That's a conjugate of x because it's x multiplied by something in front and the inverse of that thing behind. It's also plainly equal to x because the x and the x inverse cancel here, leaving us with just x. So x is conjugate to itself. If you don't like this description, you can take identity here and write identity x, identity inverse, which again is just x. So every element in a group is conjugate to itself. Second thing we have to show is that x is symmetric. So to show that, we have to show that whenever x is related to y, y is also related to x. So let's suppose we have a pair of elements with the property that x is related to y in this sense. That means that y is equal to gx g inverse for some element g of g. What we have to show that our relation is symmetric is show that the statement y related to x must also be true, which means x must be a conjugate of y. All we have to go on is this description of y as a conjugate of x. So let's rearrange it to extract the x part and leave it isolated on one side. So if y is equal to gx g inverse, then by composing both sides of this equation on the left with the inverse of g to cancel the g from this side, and on the right with g itself to cancel the g inverse from this side, what we find is that x is equal to g inverse yg. Okay, that's the same as this statement, just with both sides of it composed on the left with g inverse and on the right with g. That puts a g inverse in front of the y and a g after it, and it cancels the g and the g inverse from the right hand side. Okay. And then the observation is just that this is a statement that says x is equal to y, composed in front with some element of the group and behind with the inverse of that element, because g, of course, is g inverse inverse. So this is saying that x is equal to y, composed in front with g inverse, and on the right with g inverse inverse. So y, indeed, according to that, is related to x. It is a conjugate of x. And our conclusion there is that the relation of conjugacy is symmetric, that if x is a conjugate of y, then y is also a conjugate of x. Okay, that this will always be true in any group. Then the third thing we need to show to confirm that our relation of conjugacy is an equivalence relation is that it's transitive. And what we need to do there is imagine that we have three elements, x, y, z, where x is related to y and y is related to z. And we want to be able to conclude that x must be related to z in that situation. Okay, so suppose we have three elements like this. Y is related to x, that means we can write y as gx g inverse for some element g of our group. Y is related to z, that means we can write z as hy, h inverse, for some element h of our group. What we would like to be able to do would be to show that x is related to z. In other words, that z can be written as something x, something inverse. Okay, what we have to use are these descriptions of z and of y. Okay, we want to write z in terms of x. We have a description of z in terms of y and a description of y in terms of x. So let's start with our description of z in terms of y and see what we can do. We know that z is hy, h inverse. We know that y is gx g inverse. So this is saying that z is h, gx g inverse, h inverse. Okay, and I've put the brackets here to indicate that this bit is just y. We're in a group, we're in an associative situation, so we can basically kind of pretty much ignore the brackets. That's what the associativity tells us. So this tells us that z is equal to hg x g inverse h inverse. What we'd like to do would be show that z is x composed on the left with something and on the right with the inverse of that same thing. Here we have x composed on the left with hg and on the right with the element g inverse h inverse, which I claim is nothing but the inverse of hg. Okay. So if you believe that, then we're showing that z is x composed on the left with hg and on the right with the inverse of hg, which is indeed saying that z is conjugate to x and that the relation of conjugacy is transitive. Okay, this is kind of a formal proof of the statement that the conjugacy is an equivalence relation in groups. There's a slightly more informal version of the same thing in the lecture notes, if you prefer that. But what it tells us, of course, from the general theory of equivalence relations, is that whenever you have a pair of elements in a group where one is conjugate to the other, then both of them are conjugate to each other. And moreover, anything that's conjugate to either one of them has the same set of conjugates as both of them. Okay. So the equivalence relation of conjugacy basically partitions the group up into a bunch of pieces, each one consisting of a bunch of elements, all of which are conjugate to each other. These things are called the conjugacy classes in the group. We've seen that in the example of GL3R, the distinct conjugacy classes basically correspond to distinct linear transformations, invertible linear transformations of three-dimensional space, because two elements belong to the same conjugacy class precisely when they describe the same linear transformations. So sometimes conjugacy classes have sort of a powerful geometric meaning like that. They don't always, but they're always of relevance and importance in the group. What we're going to do next, and it will be in the next lecture, is relate this concept of a conjugacy class to the concept of the centralizer of an element, which is quite an important thing. And then we'll also use the machinery of cosets that we used in Lagrange's theorem in order to do that. Okay, so there's quite a lot in this notion of conjugacy, and quite a lot of connections of various things that we've seen so far together in this section. So just give it a bit of time to digest all the ingredients as best you can. Okay, the challenge for this video relates to the last assertion here, which I didn't really give any justification for, the replacement of G inverse H inverse with the inverse of HG. So your task and the challenge this week is to explain why that's a reasonable thing to do. So in the proof that conjugacy is an equivalence relation, at the last step there for the transitivity, we use the fact that the inverse of the product of two elements in a group, think of product as meaning composition, the thing you get by combining two elements in a group using the group operation, that the inverse of the product of two elements is the product of their inverses, but in the opposite order. So the assertion here is that if you have a pair of elements G and H in a group, and you want to know the inverse of GH, the claim is that that's the composition of the inverses of G and H separately, but in the opposite order. Okay, so the inverse of GH should be H inverse, G inverse. Very likely you've seen this before in the context of matrices that have inverses. Okay, so the challenge has two parts. First part is to explain why this statement is true, that the inverse of the composition of two things is the composition of their inverses, but in the opposite order. And the second part of the challenge is to think of an example from everyday life, not from the world of mathematics, that confirms that statement, that the inverse of composing two operations is to apply their inverses, but in the opposite order. And what I mean by from everyday life, not from mathematics, is that I don't want an example of a pair of matrices that have inverses or anything like that, or a pair of permutations or something. So I mean operations that occur in everyday life. So, you know, things like opening a door, getting into a car, something like that. But don't use those examples. Think of your own, where you have two things, and the reverse of doing one after the other is to reverse them, but not in the same order. Okay, thanks everybody. That's it for this one. We'll see you soon.